Come back. So now we want to find the volume of the solid obtained by rotating the region bounded by the curves y equals x and y equals square root x about the line y equals 1. Okay, so y equals x is this line, y equals square root x is this curve. So you're looking at the region between the line and the curve, and you want to rotate it about the line y equals 1. That's the horizontal line. So you want to take this curve, rotate it about the line y equals 1. Notice the intersection points are 1, 1 and 0, 0. Okay, you might want to check for yourself. Set x equals square root x and solve for x. All right, you will get 0, 0 and 1, 1. Now, when you rotate it about the line y equals 1, you're going to have vertical cross sections. Your x is going to go from 0 to 1. You see, 0 to 1. You're taking integration with respect to dx because you have vertical cross sections, so each width is delta x. All right. Now what about the radius? So this being the central location, radius will be this distance. Now notice that's the outer radius. Well, from top to x-axis, distance is 1 because that's what y-coordinate is 1 here. 1 minus x is the outer radius, and 1 minus square root x is the inner radius. Outer radius is 1 minus x, inner radius is 1 minus square root x. So remember, the center is over there. This entire distance from the x-axis is 1. So outer radius is all of 1 minus this line given by y minus x. Coordinate, y coordinate is y equals x. Likewise, the inner radius, the entire distance is 1 minus the y coordinate at this curve, which is square root x. So that's how you fetch inner radius, outer radius. So cross-sectional area is pi radius squared, pi radius squared. Once you detect that, the rest is straightforward. Pi is a common factor, comes out. This is a complete square, 1 minus 2x plus x squared minus, be careful with the signs, 1 minus 2 square root x, but with the minus outside it becomes plus, plus square root x squared, with the minus outside it's a negative. So upon continuing, this is straightforward calculation. Make sure your limits are okay. Don't forget the pi outside. Finally, when you substitute, you get pi times 1 over 6. In other words, pi over 6. All right. Okay, so pi over 6. Now the last problem. Find the volume of the solid whose base is the region in the first quadrant bounded by y equals x to the 6th, y equals 1, and the y-axis, whose cross-sections perpendicular to the x-axis are squares. Okay, let's understand these details. Y equals x to the 6th. That's your curve, y equals x to the 6th. Y equals 1. That's the horizontal line, y equals 1. Y-axis, that's the y-axis. So that is the region, your base. Now, cross sections perpendicular to the x-axis, that is top-down cross sections. These are squares. So, I hope it's clear. The region is here, and that's going to be a square. So you may very well imagine slices of squares standing over here. So you would have a large square here, smaller square, smaller square, so on, so on, so on, until you are a point. So it might be difficult to visualize, but imagine this particular flat region on the bottom and squares sitting on top of it. Infinitely many squares. Large square of that side length one, smaller side length, smaller side length, and so on. So vertical cross sections are squares. What does that say? The solid has base that is bound by the curves y equals x to the 6, y equals 1, and the y-axis. So that's your base. Every cross-section perpendicular to the x-axis, okay, perpendicular to the x-axis is a square. Therefore, area of each cross-section. So what is the area of a square? It is side times side, okay. So this may look like a rectangular, but look, we are looking at it from the top. So this is actually a square. So what is that distance? Well, all of this distance from the x-axis is 1, and you have to take away a small height there. What is that height given by? So that's the y equals x to the 6. So 1 minus x to the 6 is the length of each square. So area of each square is length square. All right. So what is our volume? We are going from left to right because all our cross sections are vertical. You are going from left to right, 0 until x coordinate 1. Cross-sectional area is 1 minus x to the power 6 power 2. So notice there is no rotation, so we don't have circles. We simply have squares on each cross-section. So at this point, once you have set up the problem, the rest is simply calculation. This is a complete squared. 1 minus 2x to the power 6 plus x to the power 12 dx. Integral 0 to 1. When you take its integration, I have x, I have 2x to the 7th over 7, x to the 13th over 13. Apply the limits. Once you apply the limits, this is my final answer upon simplification. So let's check. 72 over 91. It's correct. And now that completes our problem. All right. So that completes section 5.2. Next, we'll continue section 5.3 in our next videos. Until then,